Hey everybody, my name's Dr. Robin Bond, and I'm a scientist. When I'm out and about with the general public, I like to call myself an environmental chemist because that's something that people kind of understand, but it's not 100% true.
The reason I don't like to call myself a chemist is it makes people think that I'm stuck in lab all the time, which really isn't true and doesn't really capture the nature of my work. So what I'd like to talk about today is, what do I actually do? What does it mean for me to be a biogeochemist? So I'm out here for a walk on the forest surrounding the Evergreen State College, which is where I work. And let's take a look at some processes that might be considered biogeochemistry. So here we see something that you frequently see in winter, a bunch of dead leaves. And if you look further down, the leaves are actually starting to rot. That's a chemical process, and you could call that biochemistry, which is chemical processes by which living things, or formerly living things, change.
Most of this dirt here comes from rotting leaves, rotting stuff. So what the biology does affects the chemistry of the earth. That's biogeochemistry.
So one of the things you probably knew is that the sorts of plants that grow in a place are completely dependent on what the soil's like and what the weather conditions are like. So for example, out in eastern Washington where it's dry, you end up getting very different plants than in western Washington where you get a lot of rain. So one of the ways in which knowing biogeochemistry is very helpful is we can use it to think about what life would be like on other planets. This is Jupiter's moon Europa, and I have done work modeling what the ocean under that ice might be like, but I'm not going to talk about that today because it's a little boring to show on video. Here's another planet where I've done work, not the planet itself, but it really interests me. So this is what Mars looks like now, but I'm more interested in what it looked like 3.5–4 billion years ago when there was still a reasonable amount of water. And what it probably looked like was something like this, maybe minus the people. This is actually our field expedition, and it's out in the Great Salt Lake Desert. It's a great place to go, but I am looking for something that's a little closer to home that I could visit to see what life might be like. I'm out here in Okanagan County because the geology here is very similar to what we expect to see on Mars. There's a lot of magnesium and sulfate-rich rocks, which is what the rovers have found. And I'm going to get some samples at some salty lakes that we think might be similar to what we saw on Mars. So I'm out here at Wanacott Lake in Okanagan County, and what I'm going to do now, I'm going to collect some water samples, and I'm going to collect a sample of the sediment that's building up in the lake. So what I'm doing here is I'm measuring the chemical compounds in some of the water. I have a sample that I pulled from the lake, and I'm going to use my spectrophotometer to measure how much oxygen there is in the lake water. So I'm just gonna take my sample vial, and you can see it's changed color, and the darker the blue, the more oxygen there is. So what does that mean? Let's take a look. This is my little chemetric spectrophotometer. So I put the sample vial in there and now it's going to measure. So while I wait for the spectrophotometer to make its measurement, I go down to the lake and I'm going to measure the pH, the conductivity, and the temperature. You saw me collecting samples earlier and I'm going to take those back to the lab. You might wonder why I don't measure those right here. The answer is that some of the things that we need to measure, we can measure better in the lab, we can measure more precisely. So why don't we take everything back to the lab and measure it there? So I have, for example, this bottle of water you saw me collecting earlier, which we're going to use to measure for metals. And we've specially prepared this bottle so that it's not contaminated with other metals. And so we're going to run it in our ICP-MS when we get home. That's an inductively coupled plasma mass spectrometer. When you have a sample that has metals in it, those metals aren't going anywhere. But when you have something like oxygen, dissolved oxygen, that oxygen can bubble out of solution. So you have to measure the dissolved oxygen as soon as you collect it, whereas the metals, you can wait to measure it until later. 7.908 parts per million of dissolved oxygen. So now I will write that down. So when you look around you at the landscape around you, it tells you a story. That's what I do. I look at the story. I look at what that landscape is trying to tell me about what life exists and what life could exist. That's what I do as a biogeochemist. Hey folks, I hope you liked this video. If you did, please subscribe to my channel and hit the like button.